Sunday, June 6th, 2023, about 4:30 in the afternoon, bright sunny day, following a couple days of rain, which we sorely missed when it doesn't rain anymore, or it rains too much. Monsoon or drought, not four seasons. Global climate change. So anyways, here what we've been reading about is differential analysis, and how that really reflects the continuous rates of change of things. Continuous in the sense is that the values are as from continuum, and continuous in the sense that what changes values are as from continuum. So it's usually framed in terms of the standard about the classes of functions that are defined, that that they're differentiable any given number of times before they're not differentiable anymore. That a certain class of functions called C infinity, or C to the infinity, or C infinity, the continuous functions, infinitely differentiable, meaning differentiable any number of times. And that then there has been discussion about the continuous and the discontinuous, about various definitions of integration. And up in there, Riemann's definition, and Lebesgue then, about the introduction of measure vis-a-vis Riemann's regions, vis-a-vis the old-fashioned like Newton and Leibniz, that basically reflect nothing different than Riemann's definition of integration. And about how that though followed Cauchy-Weierstrass, and then about that out of Göttingen, Germany, that there was Gauss, and there was Dirichlet, and there was Riemann, and that they kind of followed in a course, and then that Gauss then having kind of let in that all this stuff that was his apparatus of complex analysis had to be supported, kind of maintains that as baggage, into then what gets into Dirichlet and the continuous and discontinuous functions there, and then point set topology, because at this point in time it came around to be less than only geometry's world, into topology and a point set topology and various definitions. And after Cauchy and Weierstrass, then that really became the fundamental foundation for standard, what we call standard real analysis. And so that Riemann, basically following that, was the first person to say, hey, look, I formalized it in the new fashionable style, so now I have priority. And it's kind of so, because he's also, famed for a couple other different things and contributions, and bringing an entire kind of, not just a convention, and not just a convenience, and not just an opinion, and not just a happenstance, time and place kind of thing, but also kind of a surrounds of a concept about the various notions that go together that make it possible to then carry the results forward. That Riemann is kind of a signpost after, with Cauchy and Weierstrass, a ways after Leibniz and Newton, and Gregory and Taylor and Maclaurin and Newton, and then with regards to how there are other forms that establish what's today in terms of measure theory. The topology and measure theory is about function theory, is this kind of milieu of what things are continuous. That what a continuous domain is in a sense indicated by geometry's assignment of real numbers to points on a line. Points in a line or points on a line. That there's a difference between those two is for a reason. That there can be continuous domains that are kind of this Aristotle's continuum of points on a line, in a line, and the field continuity of points on a line, and then the signal continuity for Dirichlet and for Nyquist and Shannon, the modern touchstones of signal theories and information theories, theory of signals, which convey information in time, that there are these three kinds of continuous domains. and the standard has one, and then to make it so that they're supported other kinds is an important thing, because otherwise they're lacking. And there are various solutions to these various systems that are natural and geometric that are missing. So in this sense, there's a lot to be said for not so much, but a sincere and pretty unified in concept effort to make for foundations why this is so. And so we got talking about point set topology and in topoi or toposes, where topology lives, the continuous surfaces and manifolds, and about their sheaves, their neighborhoods where they have limit points and critical points, what indicate which regions are continuous, upon which where continuous functions are defined, that they as well are not discontinuous with regards to these various notions of continuity and integrability, about the criteria of convergence and the existence of measurable content, measurable character, analytical character, that makes so that the analysis is well defined, and then it ends up being algebraic, and then it ends up being geometric, and then it ends up being arithmetic in terms of the conservation of sums, and about the very particular case about that the limit is the sum. The limit is no different from the sum. The limit is a formal apparatus establishing guarantees that a given particular process or manner of speaking, a manner of bookkeeping, will have that the least upper bound of one-sided limit is well defined. Then there's that in extremis, when you take the limit of each of the limits that come back together, that looking at the differentials, the raw differential, the infinitely many differential regions on the one line that have to go to zero in their width each, while maintaining their height, and then maintaining overall their analytical character and doing the analysis, that's no different than there being infinitesimals, an infinitude of them that make a 0, 1 or measure 1.0. It's a thing. And so reading from the Fourier series book, then, we talked about Fourier's approach and about the particulars of sine and cosine as orthogonal functions, and that the small angle approximation or for sine offers one particular thing that makes it tractable, and its placement in the development of a Fourier style analysis, the establishment of an infinite series in terms of these complementary functions, what make it so that the coefficients are well defined, and then their telescoping and their scaffold they hold up. And as talked about the Dirichlet kernel then as the functional bit in the middle, about how it's gone about defining what that is in terms of that there was making a window over this whole the line that the function could be drawn across, and guaranteeing that it's analytical there, that it's well defined, and then figuring a box for that so that then this Dirichlet kernel kind of acts in the middle of that. About the interchangeability of those, if any other pair of functions can be so defined that have similar enough properties, or make and afford such an identity as makes for usual this derivation, then it could be those, or it would be for whatever the properties that those they have. It would be possible to add up some functions in terms of such orthogonal pairs of functions, and indeed any pair of orthogonal functions. It's well known that can be defined a transform in terms of time and frequency domain of periodic functions, which I don't know too much about because it's really a great and important field in signal theory and information theory, and about its widespread applications in the compression of continuous tone imagery, like the cosine transform or wavelet transforms, and that as well something like the wavelet is a particular kernel of a bunch of different types of families of functions, and so it's both the limit is bringing it down from those, and its elementary part is adding up to those, just like 0, 1 is kind of as that you can add ones together in increment and so on and implement addition out to infinity, or as well take 0, 1 and divide it into bits until finally it's infinitesimals. Not that those complete, but that's their limits. Then that those complete is available to deductive analysis, which has that Zeno's paradoxes of motion are resolved by this deductive analysis that makes it so that the limit is no different than the sum, and the limit or value is not reached by any finite element analysis except in the limit, but that is as it is reached, then it's no different than the sum. This adds a lot of security in a sense, and when I say that, it's to be kind of clarified that one of the entire strengths of the standard and its rigorous formal interpretation is that it's unambiguous and uncomplicated by anything infinite, truly infinite. It's only delta epsilonics, and all the results are based about getting back down to 0. And the fact that in the existence of a field, there's no 1 over infinity, but still that this delta epsilonics makes that it's always, there's something arbitrarily small, yet non-zero. And so there's a certain security in that, but there's a certain ignorance or where the sidewalk ends for that also. And there is certain security in having the concept of the Aristotle's continuum or Zeno's continuum, not just Zeno's paradox, but Zeno's continuum, which makes for the field where his exercises in motion occur in real time and constant uniform time. That is better. And with enough particular notions about what is and isn't inferable and deducible, reasonable, what's sensible from these things, it doesn't take too much bookkeeping to ensure that these models of continuous domains are each complete themselves and necessarily existing, replete together, and that only having one of them is insufficient for general analysis, that any given form of a differential system can see arise. All right. Well, so I haven't read this book before, and chapter 3 gets in Return to the Heated Bar, which is about it's the theory of heat and the distribution of heat. The idea was that heat always transfers from a region of a higher heat to a neighboring region, a nearest neighbor, an instantaneous neighbor of less, until such time as they're equal, in which time it becomes either that region is still spreading out to a further region, or that otherwise vis-a-vis this dissipation and attenuation, that it goes flat to an equilibrium. There's not in the model the notion of oscillation like a heat bubble or a heat blob. idea being that in something like the atmosphere, of course, it's not just pure heat, but it's carriage, is via convection in currents of air, and as to how it's organized, that it would not necessarily just be the same, because it assumes an isotropic media that that a body of gas is not. And so here, a wire or a bar is basically, for a metal, the closest thing there is to approximate a uniform isotropic media for the transmission of heat. And it doesn't take into account anything about the radiation of heat in the infrared, or that there's convection and there's conduction of heat in the isotropic media, and there's convection of heat when it transfers from body to body into to where something like a gas or liquid will then react from that and gain heat or lose heat and this kind of thing. Anyway, it goes back to talking about the boundary value problem, a continuous function u from this bar D, which is for x and t and r squared, x is between 0 and a and t greater than 0. For this differential function, class is C2, so it could be C inf t, but it's C2. At least twice differentiable, and then it sets up the Laplacian, which is the second partial derivative in each variable, Cartesian variable, Cartesian coordinates, and where the harmonic function is where the Laplacian is 0. But anyways, that's C2. Satisfies the heat equation in D, where the heat equation was based on this conductivity and the capacity of they end up defining the isotropic media's material properties by numbers, and so end up being constants in terms of either the specification of material or the measure of a material, that according to this equation in the model, both it's measurable and it's predictable. That and again, I'm just kind of looking backwards to find where it exactly defines it. The heat equation. Thermal diffusivity is K equals kappa over C rho greater than 0, where C rho is a uniform cross section whose area is denoted by A and constant density rho. The temperature varies so smoothly in time and along the bar that the function u has continuous first and second partials derivatives with respect to both variables. At any given time t, all the points at abscissa t have the same temperature denoted by uxt. And the bar is insulated along its lateral surface. There is no exchange of heat with the surrounding medium through the surface. So that would be kind of like a perfectly reflecting layer that also is an absolute insulator. So then the heat is in the slice, the heat is the quantity, and kappa is the thermal conductivity, and derived from that, K equals kappa over C rho, thermal diffusivity. That U sub T of xt equals Ku xx xt is called the heat equation, or the diffusion equation, because it just models this diffusion, and it happens to be in a quantity that's called heat. That what would otherwise entail from some of the other notions of different models of like fluids or mediums, for example, of that the the electrophoresis of gel electrophoresis is an experiment in biology. And what it does is it basically establishes for a given kinds of gel that electrophoresis is a property that drives the propagation of various different sizes of molecules of proteins in the slab of gel electrophoresis. So it kind of diffuses according to an equation. And so what's determined of that is you can tell what are the size of something like when you're doing shotgun or DNA amplification or something like that, as a usual freshman lab in molecular biology, is that gel electrophoresis is just a similar kind of thing with the model of diffusivity or dissipation and attenuation here. That diffusivity and diffusion is a model of dissipation. While at the same time it expands its area that it's in, it decreases in value wherever it is. It doesn't have a natural tendency to reconstitute, to restitute or reconstitute or oscillate. That's just an example then making for what would be constants to care about. Then besides that, it got into the separation terms for T and X and solving either way by putting the constants up and out so that they both have trivial solutions. That's one thing, and it can be framed in terms of diffusivity, which can then be framed in terms of some kind of general dissipativity. That's pretty general. And for continuum mechanics and mechanics of the flow of things and the transits of things. Then another idea about this is that the notion that the flow is always positive at any one time has that if you think of it as kind of like a liquid slowly filling a hose and expanding it as the pressure goes on with it. So like a thick or viscous liquid filling a hose, and so that over time that the pressure would be kind of uniform where it goes, and then it would just slowly inflate that section of the hose. Now, but if you imagine that it might have a very fine particles in it, then those could flow around in the, well, that overall the body is viscous, that internally the body is not that it's viscous and solid, but that it's superfluid. Now why am I kind of kicking out the jams on this or staking out, these exterior products outside of the model? It's because then what it results is that in similar notions of the same kind of equations for flows and stuff, it ends up becoming relevant when there are vortices or eddies, or that otherwise that in an isotropic media and a constant input, a source, it's expected that everything is kind of is one way. But anything that has a natural process sort of has that it settles to its equilibrium. And so there's almost always a notion of the restitutive in the dissipative and vice versa. The dissipative is the usual notion in the restitutive because there's no perpetual motion machine, because there's nothing that's 100% efficient in transforming energy among various representations or states, thus that someone's always lost. There's no perpetual motion machine. It's similar with the dissipative. There's never a perfect pour, or there is, but there's never a splashless dive or something like that. That there's always some kind of reconstitutive or restitutive in the oscillating that's associated with the outside of that as well. So here it's just making that when we have our heat equation and what it models, that is then associated with this general form of the oscillating and the attenuating which one of those vanishes in terms of an equilibrium being reached as either having exhausted all the potential energy, or having reached an astable equilibrium where there's the exchange of energy maintaining over time potential energy. Rest exchange. So that's just kind of a usual idea about the whole formal apparatus. That then is reduced back down from that. It's just in terms of these two variables. It's an equation in time and location, that for a given location, according to given time, this bar has given heat at any given point. So that the idea is that it can be measured at any given point, and that's what it is, the observable. And it's so where the at any given point, this differential system will have a solution that could be not just the usual linear, closed, completely linear functions of this Fourier style analysis, which figures out a heat equation, but another one that has these more general components would still be a solution, even though it has what would be vanishing in the one way or the other, these things. This is again just sort of attaching this notion of the complementary duals to make for these completions of the space the completion of their openness and closeness. Here is a general interpretation of systems in physics. And it's such that u of x sub 0 equals fx for x between 0 and a, where f is a given continuous function representing the initial temperature distribution on the bar. However, in some applications, it is convenient to model a given physical problem using a function f that is only piecewise continuous. And for this reason, we shall modify this problem as follows. Find a function u from d bar to r that is of class C2 and D, is continuous in the set d naught equals xt in D, t, and satisfies u sub t equals k u sub xx. So the first partial of u with respect to t equals k u sub xx, so they have no interactions. It's differential equation in terms of k. If you could almost remove the parameter t, except as just a real input parameter. But it's what it is. It's so separable, and it has initial conditions that the beginning and the end of the bar is 0. And that u of x comma 0 equals fx, and u of x t goes to fx as t goes to 0. So this is almost like, well, what do you have to input to the bar to program it that the heat's in the middle, and it's like so. The f is a given piecewise continuous function. Note that u cannot be required to be continuous on D because now f may not be continuous on 0a. Instead, we require that u be continuous on D naught, and the meaning of the new condition is that u should be a continuous function of t at t equals 0 for each fixed x in 0a, at which f is continuous. So then this seems to be looking a way to set up the diffusion thing to split it up. And it'll be similar to some of these other ways that we'll talk about the endpoints, then we'll talk about an infinite series between them. And it will be another argument of windowing and bounding, and it's kind of the idea, this is what I would guess, not having read this yet, but that this chapter is going to get into this establishment of what's called a piecewise discontinuous function that's pasted all back together, right? And then that it's going to be used as that to say that, well, this still maintains our scaffolding from before, even though if you were to kind of have put this into place, then it wouldn't really make it so, that you were relying on the fact that whoever makes use of the limit always computes the entire sum, if this is to be like so, but otherwise the error term could, A, the error term could not vanish, and B, the error term could blow up. and see that the error term could dominate and actually reflect what is the nonlinear part of the formula. So then there's talked about a constant times e to the negative n squared pi squared kt over a squared sine n pi over ax satisfies the heat equation and the endpoint conditions. Then the initial condition becomes fx equals the sum of the cn's sine n pi over ax, shown in chapter 2, wherever f is continuous. Require f to have one-sided derivatives, then apply theorem 2.5 to its odd piecewise continuous periodic extension to R, period 2a, or scaffolding, where theorem 2.5 was the Fehler current, oh wait, that's a lemma, was the Dirichlet theorem 2.5 that this is from the left and the right and the discontinuous, that the Fourier series converges to the midpoint of the jump at those two. So the Fourier series isn't really continuous, wherever there's a piecewise continuity, then there's kind of two discontinuities in the Fourier with a point in the middle. And not just the Fourier, but in the Fourier style and how it's built up is about the existence of that value. Vis-a-vis that otherwise from the left and from the right, it says from the left and from the right. So the preceding work suggests that under these conditions on F, the sum of 6, where the Cn are given by 7, which is this the sum from 1 to infinity of the C sub n e to the negative n squared pi squared kt over a squared, or e over Cn e to the n squared x, or rather ft, I suppose, sine n pi over ax, the sum of those, so that involves a series in the power analysis of the exponentials to negative powers and to the higher order negative powers, or a power series in E. Considering that the rest of it can be kind of brought out as a function of t. That preceding work suggests that under these conditions, the sum of 6 with Cn given by 7 is the solution of our boundary value problem. However, all we know about the series 6 at this point is that each of its terms is continuous in D, is of class C2 in D, satisfies 1, 3, and it converges at each point of the form x naught and x, or x comma 0 in D, and its sum satisfies for it every x at which f is continuous. What we do not know about the series 6 is whether or not it converges for all xt in D. Its sum, if it converges, is continuous on D naught and of class C squared in D, and its sum, if it converges, satisfy 1, 3, and 5. Now, it's interesting that the author, when we talk about it's converging, that we say its limit exists if it converges. That he refers to it as the sum. So I appreciate that, because, as I was just kind of pointing out, it's a usual conceit that the limit is no different than the sum. And it does involve the sum of infinitely many areas usually vanishing in the higher order, and that it's well defined. So I'll say, it may seem very discouraging at this moment that we've worked so much to advance so little. However, this is only an apparent setback because it turns out that the most difficult of the problem, part of the problem is to prove 4. We have done that, where 4 is that this c sub n sine n pi over a x equals fx. That's sum. But that's the notion of the Fourier series, kind of. To deal with the rest, it would be helpful to answer some more general questions, such as 1, is the sum of a series of continuous functions itself continuous? And 2, is the sum of a series of differentiable functions also differentiable? And if so, can we obtain its derivative by differentiating term by term? These questions are taken up in Appendix A, in which, in order to provide some affirmative answers, we shall find it necessary to replace the ordinary concept of convergence with that of uniform convergence. So this gets into various tests for convergence, various conditions for convergence, and for stronger forms of convergence and uniform convergence, and when it's necessary to let that out, and why it's necessary to consider that some convergence tests are only affirmatory but not necessarily negatory, i.e. some convergence tests establish cases where the limit does exist, but they can't necessarily establish where the limit doesn't exist. So there are some tests for convergence for what some are considered convergent series that only are probables, or only in the affirmatory, and vice versa. For example, usual proof of divergence is a proof of the converse of a proof of convergence. No, it's but a proof of convergence is a proof of not convergence. So he proposes proposition 3.1, the series 6 converges to a function that is continuous on the set satisfies. And he says, by the choice of the coefficients, the series 6 converges and its sum satisfies. By the Riemann-Lebesgue theorem, Cn goes to 0 as n goes to infinity. And there's a positive constant m such that the absolute value C sub n is less than m for all n. I don't know. That's a hard one to say, because I suppose I'd have to refresh my understanding of these coefficients, because for an arbitrarily high negative power input, it could be arbitrarily large. And so I would say instead that there's a constant m such that C sub n is less than m for C sub I less than n. And that, and so that for a larger one than that, there's another m, and a larger one than that, there's another m. So why is this not the same thing as saying for all, even though that a usual kind of delta, for a delta epsilon x, this is usually like there exists there exists more than infinitely many numbers, or there exists arbitrarily large numbers, and for those there's an arbitrarily larger number. So just like delta epsilon x, you'd have it like so, to say it's for each instead of for all. They're two different things. Now they both suffice in a one-way case. They don't necessarily both suffice where it's antithetical, where it's not that's the condition that's held up by scaffolding on the other side. I.e., it's one thing to make a soap bubble, it's another one to make it as of arbitrarily long, because it's tenuous in the one sense and barely holds on in this one way. And so when it's so that it's otherwise also contracting that as it would, then that's fine. but it's just an example of this manner of speaking that the author could have been more precise to explain that there's sort of a reverse delta epsilonics. It's not like we say, oh, there's an arbitrarily small infinitesimal and it goes to it. Or here that there's a sufficiently large constant for all of them. It's that for anyone there is a larger constant in this. So he establishes this inequality in terms of this arbitrarily large constant. And but in a manner of speaking, this has to be in a manner of speaking, because there's conditions of the left-hand side and the lesser side of this inequality where it's not so. Though it's figured that because the coefficients must be vanishing, and again, I suppose I might necessarily have to make sure that I adopt the same definitions of convergence and lack of divergence. But it's a thing for a pretty general definition of convergence and divergence. And that it's always held up that what diverges does not converge and what converges does not diverge. And then in terms of the pathological, or that though it's not, you can't be shown whether it converges or diverges, the infinite sum of the infinite series, it either one or the other, or establishes an oscillation in a certain bounds, or in the real infinite case it goes to 1 or it goes to 0. In the laws of large numbers and the laws of small numbers, for the definitions of convergence and the criteria of convergence, according to the quantities, these are as symbolic forms, and the quantities, these are as free variables and their parameters, and the quantities, these are of reformulations, the implicit and their parameters. It's an overall consideration of the thing. And it just reflects a little bit that it's not too much more to make abstract the entire class of these derivations, when the idea is to figure out what the derivations do and mean, to make them interchangeable and themselves sensible and fungible and tractable, to get the derivations of the quantities into a common place, that then for this very general, in terms of the convergence and the sums, but here almost entirely about the convergence of the infinite series and divergence, that it's set up for them to be framed up together. And then in terms of these very particulars and what they do to affect then for what this tool from the toolkit grab bag can be used with other aspects in a derivation, according to the tenuous nature of it, of the tendencies and the propensities, the pendulous and the tenuous, that these become part of the analysis of this descriptive differential dynamics. So he establishes that this inequality holds for xt and dt naught and all n, and he says, but the series of numbers, the sum equals 1 to infinity m e n pi squared, negative pi squared, k t naught over a squared, converges by the root test, one of the tests of the criteria for convergence, a test, and then 6, that sum of the coefficients by that converges uniformly on d t naught by the wire stress n test. Since T naught, and then this is read off in the Appendix A, says, so Appendix A will offer a brief overview of well-known common tests and criteria for convergence. Since T naught is greater than 0 is arbitrary, it converges on D naught, and since we showed above that it also converges for T equals 0, we have proved that 6 converges on D bar. Since T naught greater than 0 is arbitrary, I think that's the at least arbitrary in terms of the parameterization and the implicits and that go into making for what way it could be that otherwise this series does not diverge, because the quantities are so contrived that they line up to amplify or carry over. That's part of the existence and uniqueness of the differential equations and their well defined behavior in terms of these various points, and then about their possible values and what then those are in terms of both constants and the implicits or functions, including what are derived by these contrived ones, or the feedbacks that arrive at these special cases or pathological cases. That's what's going on. In terms of then that, when it's so proven, then it can just be let alone. And as far as those usual conditions and concerns hold, then it's expected, and then there's nothing so contrived in this experiment reduced to its very simple particulars of this dissipativity in one dimension, according to some constancy of rates across it. That then, though, when there's various changes to that, like now it's no longer reflective, now it radiates or is radiated upon, or this or that, or it's the environment. Those would go into various of these to help explain why they can be so. Or we need to set it up so that all these firecrackers go off at once. This is the kind of thing that it gets into in terms of how that can be driven by a pulse, that then according to some thing that changes in time, that the function of it according to time is so defined, so that then according to this differential system, that goes to 1 or 0 respectively, where then that just becomes a uniform thing. A lot of that was read from the nonlinear electromechanical effects and applications from Mogan, where he helps describe the surface acoustic wave transducer, and about the implicits or the reformulation, the auto-parameterization, self-parameterization, what the inputs or parameters to the system have to be as functions of themselves, that having differential quantities that blow up or vanish at very contrived rates, that make it so that then the system has very particular behaviors in terms of driving up the ridge, or what otherwise would be figured to make it so that besides the underlying condition of the simple model, that the outer model has the same solution, most of the solutions in the outer model would fall off the ridge. Most of them. So, is that for kind of just beginning to read a little bit about what's going on with this notion of using now this formula for a heat equation of Joseph Fourier and what's going on with it. Then he gets in some examples and plugs in some numbers. And shows some charts. Because of the exponentials, most of the terms in this series are negligible for t large enough. Mostly. There's a movie, and it was called Aliens, and in it Sigourney Weaver plays Ellen Ripley, and in Alien it's set in space, and they went out to space and discovered these xenomorphs, and they killed an eighth of crew and took them over, and it was pretty bad. And so in Aliens, or Alien 2, the Nostromo goes to, or what it was, they go to find this colony that has dropped off, and well, they had found some of the xenomorphs. And it gets later in the series that the xenomorphs are, made of people or whatever, but anyways, it's bad, and it's very high budget and production values and all this kind of stuff. Anyways, there's only one survivor of the colony, and it's Newt. this child has been living in the air ducts and vents, and so they find Newt and gain her trust, and they're trying to figure out how to defend themselves and understand what happened in the colony. And so they understand that it's all these xenomorphs, they're the aliens, and Newt says at one point, she goes, "They mostly come at night." Mostly. And so when it says mostly, it's basically the idea is mostly means by Murphy's law. Sometimes they don't. Murphy's law is that whatever can go wrong will go wrong. And all distributed systems, when you're designing for correctness, you have to assume that any link will break at some point, or any a gamma ray will, at some point in time, you have to give up on how many nines you can guarantee of reliability and uptime. So the measure of how many nines is that, well, 2 or 3 nines means it's not going to crash every day, and 4 or 5 nines means it's not going to crash this year. And then it gets into various notions of risk and cost, and how long it takes to restore something or recover, or how much money it costs, or how much damage it will cost if something goes wrong. And in terms of what's reliability and estimate of the survivability of some formula, some function. So Murphy's law is that basically you always have to aver that the rate at which an error will occur is non-zero. It's greater than 0. And that for whatever reason, whether it reflects a transient error mode, as in a hiccup in the network, a gamma ray flipped a bit and now it's gone, vis-a-vis the core melted or the disk melted, or the network's down, or up to 5, 6, 7, 8 nines is when a dinosaur killing asteroid hits the Earth and it's all down. So anyways, when we talk about mostly, that's why there's all this stuff that goes into mathematics and the guarantee of the convergence and the existence of solutions, and then about their uniqueness, that they also exist and aren't, for example, another oscillatory system between those two, that they exist and are unique as numerical solutions. That mostly means mostly, and it can mean even almost everywhere, but does not mean a sure thing. So he says, in fact, if we define alpha equals epsilon, or rather Euler's constant E, natural logarithm constant, negative 0.00128 pi squared, about 0.987, we have from this example that it equals this expansion of u of x sub t is approximately 20 over pi of in terms of sine for t large enough. And then it shows various shape curves of the u of x at various points, and about how it rises on the middle and is less at the ends, but it still has in every one where it rises and then falls. Over time, till eventually it would be flat. He says, we now return to the value problem originally posed. That is, the original temperature distribution F is assumed to be continuous on 0A, and we want to show that the series has a continuous sum on D bar that satisfies the initial and endpoint conditions. In view of the preceding work, all that remains to be shown is that the sum is continuous on D bar. This would be an immediate consequence of theorem 8.4 if we show that 6 is uniformly convergent on D bar, which in particular requires its uniform convergence for t equals 0. Thus the question we face now is, does the Fourier series of a continuous function that also has one-sided derivatives converge uniformly? Clearly, this question could not have been answered in 1829, when Dirichlet first proved the convergence of Fourier series, as the concept of uniform convergence, and kind of like here we've been talking about general convergence and divergence, had not yet been discovered. As it is, the same question was posed by Heinrich Eduard Heine, a professor at the University of Halle. He was not concerned with any kind of heat problem, but rather with the following theoretical question. Knowing that the Fourier series for a continuous function f from negative pi to pi to r that satisfies the conditions of 2.2 and has Fourier coefficients a sub n and b sub n, he asked whether or not this equality is also valid for the same function, but replacing the Fourier coefficients with a different set of constants a and b. So here this is kind of has been discussed a little bit about these other possible states of the things, and about how we've been talking about the notion of the uniqueness of the limit of the Fourier series, and whether or not then that represents a unique function according to one that's arbitrarily contrived discontinuous maybe is not so. And so that gets into why these notions of this the uniform convergence is getting up to one way to talk about scaffolding and the telescoping and the discontinuous is to frame up uniform convergence, a stronger property than convergence for a given system of functions that, when completed as an infinite series, their sum form a function in this manner, where their constants are arbitrarily small or large, as are the orders of the powers that are power series, or the coefficients of their the periodic functions when this series is either in it's either in a variables greater than 1, between 0 and 1, as of the exponential, or periodic. And so then they reflect for all these different infinite series, how they're like power series, that then generally then for the periodic, that would just be to the n0th power or whatever, but that those would carry in the coefficients as of the power series. So that's what's going on here. And then he says, he asks whether or not this equality is also valid for the same function, but replacing the Fourier coefficients with a different set of constants a sub n and b sub n. Heine was at this time far from the Weierstrassian world at Berlin, but he had been a student of Weierstrass and may have learned about uniform convergence before leaving Berlin. Or he may have heard about it from a new arrival from Berlin, Georg Ferdinand Louis Philipp Kanner, who had become a privat docent in 1869 at Halle. Whatever the case, Heine knew about uniform convergence and about Weierstrass's proof that a uniformly convergent series of integrable functions can be integrated term by term. He also knew from Fourier's work, as we have shown in this, that if the equation above holds and the series on the right can be integrated term by term, then the coefficients are uniquely determined and have the values given by definition 2.1. Heine made the connection between these ideas and stated that if a function f negative pi to pi onto r is the sum of uniformly convergent trigonometric series of the form given above, then its coefficients are uniquely determined and happen to be the Fourier coefficients of f on negative pi to pi. According to all what's available to that. It was in this manner that Heine posed himself the question, when does the Fourier series of a function converge uniformly? He provided the answer in a paper of 1870, a particular case of which, sufficient for our purposes, stated below. Heine did not work any further on this type of problem, but it was he who encouraged Cantor to pursue the question of the uniqueness of the coefficients of a trigonometric series when the requirement of uniform convergence is dropped. Cantor's solution of this problem and his consequent discovery of the theory of sets have already been described. Well, that's interesting. I imagine we'll pick up with Heine and then Borel. Heine-Borel is the usual theorem after Cauchy-Weierstrass or whatever that we'll get up into at some later date. Oh, here's a footnote. It is interesting to mention that in order to complete the research in his 1870 paper, Heine introduced two concepts that are now indispensable in modern analysis. So I will look at them and turn them over and see, make sure they stand back up. The first was uniform continuity, more precisely defined in a follow-up paper of 1872. So here we're talking about continuity rather generally, and convergence. But here he says uniform continuity. So I'll be curious to see what that is at all. The second was the observation that if a closed and bounded interval is contained in a sequence of open intervals, then it is contained in a finite number of those intervals. I don't know about that. This fact was formally proved in 1895 by Emil Borel and named the Heine-Borel theorem in 1900 by Arthur Schonflies. The theorem, currently known by this name, does not require the original cover of a closed and bounded interval by open subsets to be countable. Generalization proved by Lebesgue in 1904. Eventually, this covering property of a closed and bounded set by open sets became the modern definition of compactness. It's given by Pavel Sergeyevich Alexandrov and Pavel Semyonovich Urison, or the Urison's lemma will become relevant. So the idea there is that's about the open topology, because the open topology has about that it would only be consistent with that for that to be so. Because otherwise, when you get into where, like, according to least upper bound, the least upper bound of what you could call open things rationals, open subsets of rationals in an order, are there can be infinitely many of those. That they don't contain an upper bound. That otherwise I'll have to look at this a little bit, because there are various notions about point and infinity and fixed point that have to do with compactification, which even gets into whether or not the natural integers are compact, that they have a compactification or the fixed point, and there are models where they do, and those are not standard, and there are models where they don't, and that's standard. So all the fields that deal with these things variously, like number theory and its point and infinity, and topology and other topologies, unaccountable topology, for example, or otherwise, hyper topology, just as examples, or anti-open. And then for these various other aspects of what become non-standard, here I'll be very curious to find out a little bit more about how to apply that in terms of what's called uniform continuity. But I think the author meant uniform convergence. I kind of do. But I'll be looking for something particularly about that, because pretty much continuous domains and continuity is not defined in the standard. Continuous functions, yes. Continuous domains, no. But here there's something to be said for it, and how it can be so in terms of any topology that it's so. Or in a topology theory, a function theory, and those that one or the other of it holds, or both. These are the kinds of things we'll get to later. Or I imagine need further analysis to give a deconstructive account for them, why they do or don't hold, and where together they could outrace each other or scaffold each other or not. These are the kinds of things that beyond the standard, of course, because first we want a standard that stands up, but then secondly we want a replete foundations that advises the edge cases, the corner cases, and especially when it becomes that the well-defined, well-behaved, guaranteed behavior of these systems is outside. That the total field theory of this theory of some potentials has a solution. These are the kind of things we get to. Well, all right, hey, have a great day. I hope.